Okay, and I'm gonna go ahead and share my screen. Let's see. All right, would somebody let me know if this is visible?
Yeah, we can see
Yeah.
it.
Okay, I appreciate it. Thank y'all. Okay, so this document right here, I'm gonna go ahead and copy this link and I'm gonna put it in the chat. Uh, so make sure that y'all can access that and open that. Tx.ag/221 exam 3. So this document was compiled last semester. So this is not my work. This was done by the former TAs, but I think a lot of this material is really, really helpful. Um, I'm not going to be going over these PowerPoints today, um, but I think all of this information, with the exception of maybe skip lists, I think should be relevant to the exam. So priority queues, unordered maps, and hashing, well, admittedly, I think will be a minority of the test still on there. Graph basics, graph representation, traversal, sorting, and then shortest path, spanning trees, and then greedy algorithms. So uh, if y'all have extra time to review beyond what we're going to do today, and you need even more practice, go ahead and look through all of these slides. I will say, like, if you click on, like, I don't know, if we click on one of these, what I really, really do like about these slides, I think the most useful thing that you're going to get from these is explanations of runtime. So I guess it's not on this one, but on some of these slides, they'll have huge tables of like, here's this algorithm, here's the running time under this condition, this condition, this condition. And that's going to be like 30% of the test usually. So, um, on your own time, if you're unclear about any particular topic, go and do a spot check, memorize the run times, super important. Also, I think this is probably, again, what a lot of y'all want to know is what is the FRQ going to be like? So this is just a list of maybe starting points for you to practice. So if you have some time on your hands, try solving one of these problems and see how you feel. If you do it immediately, maybe you're good to go. If it takes an hour, maybe you want to study a little bit of coding on your own time. Again, I'm not going to be doing actual coding in front of y'all because Josh made this video last year. So if y'all check this out, uh, okay, well, I'm not actually going to watch the video. But this is Josh goes over how to do BFS and how to do DFS using starter code that is very similar to what y'all will see on the exam. So please watch this video. It is excellent. Josh is wicked smart. Everything in that video, absolutely worth your time. And the way I see it is you can either figure out how to do BFS and DFS now and spend that time figuring it out now, or you can show up to the exam and try to figure it out during your exam time. So I would do it now if I were you. I think the exam is going to be 80 minutes. So yeah, maybe do one or two of these, probably. Okay, so before we get started, any questions? It's clear what is expected. Okay, well, I certainly hope so. So I'm gonna go ahead and I'm gonna switch to my iPad. Uh, and once again, can someone confirm that this is visible?
Yeah, we can see it.
Okay, thank you, man. Appreciate it. Okay, so today what we're gonna be covering is I'm just gonna briefly summarize. We're gonna be looking at traversal, so we're gonna be looking at the difference between DFS and BFS. We're going to be looking at strongly connected components, how that's defined, and maybe how you would go about detecting this. We're going to talk about DFS edge classification and in what scenario you would have the different types of edges. We're going to talk about topological sort with a depth first search implementation. In the PA, y'all were expected to do the in-degree implementation, so I assume that that's good. I assume that y'all understand that. We didn't talk about this, but I think I've seen it appear on one or two test questions, so probably good to cover it. We're going to be talking about priority queues, the different priority queues. We're going to do a quick recap of the binary heap. It's not terribly hard. We're going to take a kind of in-depth look at Dijkstra's algorithm, kind of the different scenarios that you might see in Dijkstra's algorithm, as well as what these runtimes are going to be. We're going to talk about what the time complexity is in different scenarios. Then we're going to actually run Dijkstra's algorithm, and I'm going to ask like some test-specific questions about Dijkstra's algorithm that y'all might see based on the output of this table. And then we're going to talk about minimum spanning trees. So we're going to start with Kruskal's algorithm. And again, I'm going to try to, maybe hint at some information that you might need to know for the test. And then we're going to talk about the running time for that again. And then this example probably will do prims maybe if we have time and y'all are still feeling up for it. So without further ado, let's talk about DFS and BFS. So I think before you really understand graph theory or graphs, DFS and BFS, these are kind of like the foundations. So before any of the other algorithms or any of the other theory is going to make any sense at all, I want you to have a solid understanding of how to traverse a graph. So what I've done here is I've drawn an undirected graph. And as you can see, I've made two identical copies. It's the same graph. And I'm going to walk through both depth first and breadth first search on this graph. And the point that I want to make is that the algorithm is identical, with the only change being what data structure you use to traverse the graph, right? So if you traverse the graph, storing the children of whatever node that you just explored in a stack, you get DFS. And if you store them in a queue, you get BFS. So as you can see, right now I have written out the path that DFS takes. This is not unique. Could potentially have more than one path, but as it stands right now, it looks like we start at A, and we make our way through the graph kind of like this, and then see E goes down here. Kind of like that is the traversal that we're looking at right now. And again, this could be different depending on just some random choices that we're going to make. But yeah, when you see DFS, I want you to think stack. And so after this review, again, please go watch Josh's video because that'll make this quite clear. Okay, so when you're doing DFS, you have to arbitrarily arbitrarily pick a node to start at. So for this example, I'm just going to arbitrarily say we're starting at A, just to keep it simple and consistent. And I'm going to mark that with a 0 being the first thing that we've seen. And I'm going to put a slash next to that 0 because DFS will terminate when we get back here. So when you're doing DFS, this stack right here that I said was like, this is the important fundamental concept behind DFS. This is implied. It's an implied stack. And what I mean by that is that you're going to be using recursion usually when you're implementing DFS. So instead of having like a literal explicit stack right here, what you're really doing is you're making recursive calls. And I'm just going to use this stack to keep track of where those recursive calls are going. So let's just randomly pick the next node that A is going to. As you can see, we could start DFS this way, or we could start DFS this way. I'm just going to pick B because I feel like it. And so the next thing that we're going to look at is B. Oh, and by the way, I'm going to be putting the nodes as we call DFS in the stack. So we're going to look at B. I'm going to label that with a 1, and we're going to put it in the stack. And so the rule for DFS is before you can finish processing a node, you have to finish processing all of its children. And we're going to see that as we accumulate nodes that have children that need to be processed, we're going to fill up the stack. So B is not done because we have to call DFS on its child, which is D. So that's here, and we're going to push that to the stack. And then let's say D goes to, again, here we could go to E, or we could go to F. But I think in the example before I went to E, so let's just stay consistent. So we're going to push E to the stack. And as you can see, we can't say that E is finished until we visit all of its children. The first of which is C. So let's push C to the stack. And so here's a point where DFS is actually going to terminate, right? Because calling the DFS on all of the children of C is trivial because C doesn't have any children. So we can effectively just turn around here. And we can say that that's done. So as soon as we process a node, we remove it from this recursive stack, right? Because it's done. And we continue, let's see, it looks like the next thing on our stack was E. So we continue checking the children of E. So let's do that. So for E, the next child that we need to visit is either F or H. I'm just going to randomly pick and say that we're going to H next. So push that to the stack. H looks at F, So push this to the stack. F can find G. G terminates, so we remove it from the stack. Let's see, now F is the next thing on the stack. We've seen all of its children, so we can terminate that and say that this is 10. H is now the next thing on the stack. We've seen all of its children, so we're going to call that 11. Let's see, now we're back at E. We're going to remove E from the stack, and we're going to call that 12. We're going to remove D from the stack. I'm going to call that 13, and then 14 and 15. So hopefully, while this explanation was rather slow, this gives you some intuition as to why DFS traversal is so inherently tied to this data structure, right? It's the stack that is like, this is the magic behind DFS. This is what causes it to go in the order that it does go in. And then also worth note is that DFS is going to have this runtime. That's super important that you understand that. Don't just memorize it. Take a second to think about why that is. Okay, so I made a claim earlier that the only difference between DFS and BFS was the data structure that you use to traverse. So as before, we used a stack. BFS, its bread and butter is the queue. So here as soon as we had explored a node, we pushed it to a stack and then continued traversing until the node finished terminating. Here in BFS, we're going to do the same thing, but we're going to put our nodes into a queue. And as you can see right here, from having run the example already, you can draw concentric circles from wherever the starting node is, and that's going to tell you kind of like the degrees of separation that the starting node is from any other node. And as you can see, first we're going to look at A, and then we're going to look at the children of A, and then we're going to look at all of the children of the children of A, and then the children of the children of the children of A. And so instead of traversing the graph kind of like going deep into the graph before we've actually, seen all of the children of A, we're going to kind of uniformly radiate outwards from the starting node. So let's go ahead and reset this example. Okay, so let's say, and this is our queue, by the way, right here. So this is our queue. Let's go ahead and say that we're starting at A once again, and I'm going to go ahead and draw that here. And so we're going to add A to the queue. And so to terminate A, we just have to look at all of its children. So the children of A being B and F, we're going to add those to the queue also. And we're going to pop A. So what we've done essentially is we've popped A, and we've added the children that exist in this first inner ring. And so now the next thing we're going to pop from the queue is B. And looking at B, B has one child, and that's D. So let's add that. And I think that's the only thing that B points to. And then let's pop F, and F can see D, but it can also see E and G and H. So E, G, and H, add those to the queue. And as you can see, we have just drawn the next concentric circle. So that's going to be here. Yeah, here. Yep. And then for our last concentric circle, we're going to pop D, and D has no children, so that's fine. And then we're going to pop E, and E has one child, which is C. And we're going to pop G, and that has no children. H has no children, and C has no children. And that effectively draws our last concentric circle. And thus, breadth first search is terminated. So again, this is going to have the exact same runtime because you have to see every vertex at least once, and you have to see every edge at least once. So, same runtime between these two. Again, it's important that you fundamentally understand why that's the case. Don't just memorize it. And so hopefully that should give you some intuition as to why the difference between these two algorithms is the stack and the queue. And if you didn't get that, go work through this example by hand. I think it's really foundational. Okay, so the next thing we're going to be talking about is strongly connected components. Actually, before that, if anyone has any questions, we have our PT in the chat. So Oma can help answer questions if I blew through something that is not clear. If it's really pressing that you get my attention, which is totally fine, please unmute yourself. Be happy to talk about it. Okay, so the next concept is strongly connected components. So when we're looking at a graph, Now that we know how to traverse that graph, right? DFS is the prerequisite knowledge to understanding strongly connected components. I drew this graph right here, and it's got this adjacency list that I drew on the right. And I have highlighted 4 different groups. And so a strongly connected component is defined as a graph in which every node can reach every other node and vice versa. So like hypothetically, if we were to look within one of these strongly connected components, we should be able to, and hopefully I can make this clear. Hopefully we should be able to reverse the direction of every arrow within our strongly connected component and still have a strongly connected component, right? That's kind of like, by definition, that's something that we're looking for. And as you can see, this would just be like this, right? And so when you run DFS on a graph, you might be able to discover that there are more than one strongly connected components. And so, maybe it's a little bit misleading that a graph, like if we were just looking at this region that is in this red circle, that's technically one strongly connected component. C by itself here is technically one strongly connected component. E is technically one strongly connected component. And so if we were to add more arrows, right? So if we were to add if we were to make C a strongly connected component, and into this graph or something, then we've actually reduced the number of strongly connected components in the graph. And so it's a little bit misleading because a high number of strongly connected components does not mean that the graph is better connected, air quotes, right? It just means that it exists in less little pieces. And as you can see in each of these groups, A can find any node and any node can find A, C can find itself, F, E, and G, they can find each other, so on and so forth. One of the FRQ examples that was on the doc that I showed for a second asked as a challenge, how would you actually use how would you write a program to fix this? And that's a good question. It's actually surprisingly non-trivial. So please figure that out on your own time if you're looking for a challenge. Yeah. Okay, next topic, DFS edge classification. So again, DFS being the prerequisite for this. When you run DFS on a graph, you're going to have, I think I drew it up here in the blue, you're going to have some amount of exploratory edges, right? Edges that are finding nodes for the first time. And in this case, the exploratory edges are red. I guess they used to be blue. And so what do you do with all of the other edges that you had in your graph that are not the exploratory edges, right? Like, how do you classify those ones? Well, when you run DFS, you get a tree structure kind of, right? Can you see how, like, maybe if I were to rewrite this, you've got like A, and then it points to C, and then C has D and E and F, right? The output from the exploratory edges is kind of this little tree structure, B and H. And so the nodes that don't exist on this tree that kind of break the rules of a valid, binary search tree or whatever kind of tree, we've got to classify them differently, right? So as what I've drawn in this tree, these are all of the red edges, right? If we have an edge that does something, illegal for a tree, like maybe we try to go backwards, right? Well, we have to classify this differently than the tree edges because this edge doesn't belong in a tree, right? Or maybe we have an edge that, jumps levels between two different nodes. Again, that's not valid on a tree. So we have to classify that edge differently. And then one more thing, if we have like a skip connection, again, this is not valid in a tree. So we've got to do something different about that. So I'm gonna go ahead and erase this traversal. Actually, before I do that, let's actually talk about what these edges are. So red here means tree edge, which means when you run DFS, if you discover a node on that edge, right? That edge is the first time you've ever seen the node ever. It's called a tree edge. It's also called exploratory edge sometimes. Essentially, this will form you the nice, legal, valid, pretty tree that I drew here on the right, where anything that you find with a tree edge, there's not going to be like, anything that would cause this tree to be broken in any way. Next, you've got forward edges, which I marked in blue. You can see we've got two of them here. We've got the edge from A to D, and we've got the edge from A to B. And essentially, anything that causes you to skip forward in the tree structure is called the forward edge. So from A to D, which in this case is here, or what's really difficult to see, like looking at this, like it doesn't seem like this edge from A to B would be an illegal edge, but actually, if we look at this tree right here, A to B is in fact a forward edge, right? So that's a forward edge. If we have an edge that causes us to go backwards in our tree structure, that's called a back edge. And as you can see, we've got one from I to C, which, where is I? I was after D. Did I forget to add this to this tree? I think I did. Okay. I. There was one from I to C, which, as we can see, in this case is very clearly going to be a back edge, right, on this tree. And then we had one from H to A, which again, very clearly is a back edge on the tree that used to be legal. And then, let's see, one more, we had a cross edge from E to F and from F to I. And on our tree, that kind of looks like from E to F and from F to I, that kind of looks like jumping across to a sibling of sort, right? Okay, so with that in mind, let's go ahead and do an actual traversal and see what happens. And it might not be exactly the same. So I drew out this example before. In this graph, there's not one unique way to traverse the structure, right? Because some of the nodes have multiple connections, which means that it's theoretically possible. It's theoretically entirely possible that we might do this in a new way. So if you're taking notes, be prepared for that. Okay, so let's find the tree edges first. So starting at A, let's say A goes to D. Let's switch it up. Yeah. Okay, so let's say the first thing that happens is A goes to D, and now we're calling DFS on D, which again, like it's so important that you understand DFS and understand that this is like a recursive stack-based algorithm, because that'll allow you to do things like, just running it from off the top of your head, which I think is necessary. Okay, anyways, D has one place to go, which will be here. And then I has one place to go, which will be here. From C, we can either visit E or F. Let's go ahead and visit F first. F has no more children that are unseen, so let's visit E. Say E visits G, it's its only choice. G is going to visit B, and G is going to visit H. So down here, let's draw in the actual tree edges that we just found, which in this case was looked like, if I can get both of these on the screen at the same time, kind of looked like this, and then we went D to I to C. And then from C to E and F. And then from E to G and H and B. Okay, so this is what DFS looks like. This is the order in which you actually traverse the graph. All of these are marked as tree edges. Now, what do we do about the edges that we haven't marked in yet, right? So first, let's find our forward edges. Okay, so actually, I might not be able to just pick out the forward edges immediately. This is kind of a hard problem. Let's just look at the edges one at a time and make decisions about what they should be. So first, let's look this edge from A to B. What is that? So looking down here on the graph, it seems like A to B is actually going to skip way forward in the tree. So I think we can call that a forward edge because it skips the path from A to B. So let's go ahead and say that this is a forward edge. Let's mark it in as such. And if y'all watched the Sunday review where we did DFS edge classification the first time, this example is significantly more difficult. And in fact, if y'all saw an example this difficult on the test, I think this is like about as hard as it gets for edge classification. Okay, so that's that. Let's look at C to D. C to D. It looks like an edge going from C to D would kind of be like going backwards on this path, right? From C to D is kind of against the order that we found them. So I'm going to say that this is a back edge, I believe. So let's say that. Let's see, we haven't looked at A to C. From A to C, I think this is going to be another forward edge because as you can see, it's kind of like skipping forward in the graph. Okay, so A to C, call it a forward edge. I'll mark it in as such. F to I. F to I looks like, what would this be? You're not really going across the structure. It looks like you're going backwards up to a parent, I think. So I'm gonna say that that's like going backwards in the structure. I'm gonna call this a back edge. I hope this is right. If I get something wrong, somebody unmute yourself immediately, please. Okay, E to F. E to F. Well, it looks like you kind of jump from two siblings, right? Because if C is like this parent node, then you're kind of jumping from one of the children to the other. So I'm gonna call that a cross edge. And then is that everything? No, it's H to A. And H to A, I think we can see that that's a forward edge. Okay. Okay. So again, this is like a very in-depth example of edge classification, but hopefully it should serve you well. If you are not confident about your ability to do this, list out the letters from A to Z, connect them wildly, and figure this out on a huge graph, and then you'll be able to do it for forever. I hope this is the right answer. If it's not, I really apologize, but I think so. Okay. And so I could see some let me just walk backwards real quick. So from what we've covered so far, some test questions that I could foresee you running into is like, what data structure do you use to implement depth first search? And the answer to that obviously is the stack. We might say like, how do you know when you're ready to traverse to the next node in DFS traversal? And in which case, like you have to have seen all of its children or, finished all the recursive calls. Another test question I might imagine is like asking for these numbers. So, maybe if it's if they give you an adjacency list, then these numbers are not so much of a random choice, right? Like when I'm at D, do I go here, here? Given an adjacency list, you can just, pick whichever node is listed first. And in which case it's totally fair game. A test question might be like, what are these numbers, right? Like, what are these, what's the number going to be on F when it terminates or whatever it is, right? Some test questions that I could see also like what this runtime is, that's completely fair, or maybe what the stack looks like. For BFS, some test questions I could imagine are like drawing these concentric circles, like what is the like you can drawing these circles, you can determine the distance from one node to another. So if there's a test question, it's like, would you use BFS or DFS to determine the distance between two nodes? Well, the answer is BFS, right? We've kind of drawn this like topological map almost that kind of shows you, okay, well, the distance from A to B is 1 because that's like within one concentric circle. And then from A to D, E, G, or H is 2, and the distance from A to C is 3. So you need to know that BFS is used for this purpose, and that, this is its runtime. And they might word it differently too. Like they might like wrap it in some kind of word problem. Like they might say social networking site or whatever it is, but don't worry about it. Strongly connected components. I doubt that on the multiple choice they're going to grill you on the algorithm you would use for this. They might ask questions again like, could you reverse all of these arrows and it still be fine? Or they might give you an adjacency list and say, given this adjacency list, how many strongly connected components are there, right? So, be prepared for such things. For DFS edge classification, it's pretty much the same. So they might give you an adjacency list and be like, which edges are tree edges, which ones are forward, back, cross edges, right? Or they might even show you a picture and ask you to identify, okay, looking at this picture, which one is which type of edge. So from what we've seen so far, that those are some like off the dome test questions you might have to run into. Okay, next topic, new thing, top sort using DFS. So what y'all have seen before is top sort using in degree, right? So you compute the in degree of everywhere in the graph, and then you kind of just like iterate through looking at all the nodes that have an in degree of 0 and top sort that way, which that's completely valid. Or you could top sort a graph using depth first search. So again, when I say that like these algorithms, DFS and BFS, are kind of the prerequisite to understanding any of the more advanced stuff, I'm going to die on that hill. I stand by it. You need to be able to code these two also, I think, because the FRQ is going to be more complicated than just DFS or BFS. Okay, anyway, so top sort using DFS. As you can see, we've got this little list right here that represents our output from the algorithm. And essentially what we do is we just randomly pick these nodes. I started at A. We run DFS from that node. As soon as a node terminates, we put it in the output for the data structure, right? And as soon as we have seen all of the nodes, we return the output, and we kind of intentionally store the output in backwards order, right? Like F is the first thing we put in this list, but really it should have the lowest value of top sort. Right, so the way that you would interpret this output is imagine like we gave these numbers, so 0, 1, 2, 3, 4, 5, 6, 7. So H would be like 0, C would be 1, G would be 2, right? And as you can see, like this is giving you some sort of top sort variant, right? B is going to be 3, D is 4. Wait. A is 4. And then we got 5, 6, 7. As you can see, that's a totally valid top sort ordering, and it's done using DFS, which is a little bit different. So let me actually run through that to kind of make it clear what's actually going on. Okay, and let's go ahead and clear this. So we're going to start at a random node, which again, for convenience sake, I'm going to say is A. And we're going to run DFS starting at A. So A is going to look at D, and D is going to look at F. F doesn't point to anything, so DFS actually terminates here. And as soon as DFS terminates, or you can think of it as like as soon as it starts walking backwards, that's when we're going to add this node to the output, and then it terminates at D, and then DFS gets called on this child, which is E, and DFS terminates at A. And then for the next random node, we're going to choose something that we haven't seen yet. So we're not going to, we don't need to call DFS on any of these nodes because we've already seen them because they're in our answer. So the next thing we're going to look at is B, and B terminates immediately because D has already been seen. We don't need to do any depth first search there. So add B. C doesn't need to see F because F has already been found, but it does need to find G. And then as soon as it finds G, C terminates, and then H is just doing its own thing. So that's top sort using DFS. I would have included an example top sort using in degree, but I think hopefully y'all remember how that happens. So some test questions I might see here are like, if you're doing top sort using in degree, which node gets put in the queue first? Or like looking at a graph, can you tell me which are the source vertices, right? The source vertices being the ones with in degree of 0, being these 4 in question. Or it might ask you what are the sink vertices, right? So like what are the vertices that have an whatchamacallit, out degree of 0? So in this case, it's this and this, this and this, right? So all those would be fair game. Might ask you about runtime or implementation, but you should be able to do this, I think. Okay, next topic, priority queues. So priority queues are a little bit confusing, I think. Just because a priority queue itself is not really a data structure, it's kind of like an abstract type data structure, right? Whereas like a stack and a queue, right? Like notice how we didn't have a PA called, PA3 stack and queue, right? The stack and queue, like those are not things that you implement and say like I have a stack. It's like it's not the atomic level. A stack is built upon a more fundamental data structure. And likewise, a queue, or in this case, a priority queue, has to be built on top of a more fundamental, reducible data structure, right? Like you can think like the array, or in this case, the binary heap are like, that's like the atomic level, and the priority queue is like the molecular level, right? Okay, anyways, so priority queue can be implemented based on an unsorted array, a sorted array, or a heap. And the only requirement to be a priority queue is you have to store all the data, and at any point in time, you have to be able to accept an incoming element and push it somewhere in your data structure. It doesn't matter where. And at any point in time, you have to be able to return the minimum element or pop it and remove it from the structure. So I've kind of made this table here as to how the three different implementations fare with runtime. So first, let's look at our unsorted priority queue. And this one is a little bit of a hack, right? So an unsorted priority queue, just think like you've got an array, basically. So you've just got an array, and it's just got random elements. So it could be in any order, right? And so to push to this data structure is O of 1, right? Imagine we're pushing 7. We don't actually worry about maintaining the order of this data structure because it's unsorted. So pushing is really effective, really easy, really fast. Returning the minimum element is O of n, because theoretically to find the minimum, you're going to have to like actually loop and look at every element in the data structure. So it's O of n. And then likewise, to remove that element, you have to find it. So that's also O of n. So that's the unsorted priority queue. Again, a bit of a hack, not the most efficient way to do things. The sorted priority queue is kind of the exact opposite trade-off from that. So again, we're thinking like we've got some kind of array, right? But this time it's really important that we keep all of our elements in sorted order. And so pushing is going to be expensive, right? Because if we want to push, we've got to find the next position for our element to go in. And imagine we were adding like 5. We'd have to do a bunch of work to put it there. So that's O of n. Finding the minimum element is very easy, because at any point in time, we can just return whatever is at index 0. And then pop is also going to be really easy, because say we remove the element at index 0, we don't actually have to do any extra work to maintain this sorted order, right? It's still sorted. Like this is still a sorted priority queue, even though we removed an element. Like it's good to go as soon as you pop the minimum element. And the heap, as you can see, like unsorted priority queue excels at push, and sorted excels at finding the minimum and popping the minimum. But that comes at the expense of having ineffective push and an ineffective pop, right? And so the heap data structure kind of takes the best of both worlds, and kind of just makes a compromise on both. So again, the heap is itself an array, but instead of having everything in perfectly sorted order, you have everything in heap sorted order, right? So you're guaranteed that this minimum element right here is going to be the lowest, and then you've got to follow heap rules for the rest of the stuff, which I don't actually want to do off the top of my head. But we've got an example here. So a binary heap, again, this is going to be an array. It's going to look something like this. So while it can be drawn as a tree, really in memory, this is stored contiguously, so it is actually an array. And so imagine, actually, that was wrong that I drew that. This is the list. This is like the order that we're building the binary heap in. So imagine this is like the order that you receive your inputs. It's going to shake out to a data structure that looks like this. And as you can see, the only rule for a binary heap is that every path from the root has got to be written in ascending order for, in this case, a minimum priority queue, right? If it was a maximum priority queue, it would be the other way around, right? If it was a maximum priority queue, we would be looking at something like this, where every path has got to be written in descending order. That way we preserve the highest priority element as the maximum. Okay, so really quickly, just as a refresher, if anybody if their memory has faded at all, let's go ahead and just build this binary heap and just remember what that looks like. So we've got our first element, and then we're going to fill this tree kind of in this like perfect tree formation, such that the tree is like always created the same way every time. The next element is going to be 0, and when we run into a conflict like this, we just swap these nodes upwards, right? And we continue to do so recursively until the entire data structure is fixed. So that's going to look like this, and then we add 1. And anytime we have a breach in the order, we're going to address that promptly until the data structure is once again valid. So in this case, it's got to be done again like this, and then we add 4, 5, 6. Actually, 5. That's bad. 5 and 7 would have to swap. And 8. Yeah, so that's a binary heap. Quick little review. And hopefully that makes sense as to why finding an element from, not finding an element, but adding an element is going to be log of n time, right? Because we've drawn a tree, and to add an element, hypothetically, you have to walk all the way up the tree, which is going to be log of n. And then likewise, if we wanted to remove this element, so if we remove, in this case, the highest priority, which is 0, we have to replace that with the extreme element, and then, again, walk all the way down the tree. So in this case, swapping like this. And again, this is all review, so hopefully y'all are comfortable with this by now. Calling up heap and down heap and such. And once again, sorted order. So, that's why these runtimes are what they are, because, you potentially have to walk all the way up the tree here, and then you have to potentially walk all the way down the tree here. And this was called up heap. This was down heap. Yeah, I hope I didn't confuse those. Okay. You got to have these memorized. Some test questions I might imagine for this little segment would be like asking you implementation-based ideas, right? So like if you had to implement a priority queue in one of these different scenarios, it might ask you about what these efficiencies are, or maybe they describe a scenario and you have to pick which of the 3 sorted, unsorted, or heap is the best compromise for that given scenario. They might ask you like specifically what these runtimes are, or they might give you an example of like, is this up heap, is this down heap? It might give you a list for the binary heap and say, turn this list of numbers into a heap. Or it might give you this list of numbers as a binary heap and be like, is this a valid binary heap? And in which case, you've got to actually like draw out everything in the position that it's at or whatever it is. So be prepared to answer this kind of stuff for sure. Okay, I'm gonna catch my breath. That was a lot that we just looked at. This is kind of like, I think, a decent amount of information to have taken in so far. So we did DFS, BFS, connected components, edge classification, topological sort, priority queue, binary heap. And that kind of like takes us to the next level, or what I consider. So what we have left is like the advanced graph algorithms. So we've got Dijkstra's, and this is an example of Dijkstra's. We've got Kruskals, and then we'll do Prims down here. And so if you've made it this far, you've kind of beaten the first level of algorithms, and this is kind of like, this is advanced mode for graph algorithms, or at least in the scope of this course. Okay, so Dijkstra's algorithm is a greedy algorithm that I think so I made a claim earlier that all graph algorithms essentially pretty much amount to DFS or BFS in some way. I would kind of argue that Dijkstra's is more similar to BFS than it is to DFS. It's kind of not really either of them, but I don't know. Maybe I encourage you who are here to maybe take that as a thought experiment and kind of think about how this code is very similar to BFS. It's kind of like almost a derivative of sorts. Okay, but anyways, so here's some pseudocode for Dijkstra's, and while it might look intimidating to look at all of these lines of code, I've really boiled it down to this is the whole algorithm. This is all you need to know. And so line by line, I'm just going to talk about what's happening because I think all of these lines are important. So let's define Dijkstra's algorithm to take in some graph. the graph is going to have a set of weights, right? And these set of weights respond to like the edges between the nodes. And then we're going to pick S, which is our starting point, or this is our source in the graph that we're going to run Dijkstra's from. We are going to, actually, it's confusing that I did two S's. This should be like a lowercase s right here. It's like a lowercase s. And then this one right here is like a big beefy uppercase s. So, and then also that'll be down here. So the first thing we're going to do is we're going to initialize the graph and get it ready to be traversed. So this is kind of like the solution set. There's like a solution that is going to contain our example. And then we're going to take all of our vertices from the graph and then add that to the queue, which in this case, this is our priority queue. It's not just a regular queue. So all the time that we spent up here talking about priority queues, this wasn't random. This was because priority queues actually do get used in some algorithms, this being one of them. And so while the queue is not empty, we're going to pop the minimum element from the queue. And I made a little asterisk here, so we'll come back to that. But when we're looking at the minimum element, we're going to append the element to the solution. So we're going to, add to solution set. And for every node that we can reach from the minimum, so for V and U being the minimum, V being the node that we can reach, we potentially relax that node. And I drew another star here because these are important. So when it comes to thinking about the runtime for Dijkstra's algorithm, it pretty much boils down to how many times does this happen, how many times does this happen, and then how expensive is each one. Like that's really fundamentally what you need to think about. So this outer while loop right here is going to happen. This is going to happen V times, right? Because we created a priority queue that has all of the vertices, and then we loop popping one each time. So this line is going to happen. Let me write this happens V times. This happens V times. So the runtime for Dijkstra's algorithm is going to be this happening V times however expensive this line is, right? And we'll get to that in a second. And then this last line right here, it's kind of like this little inner part, this for loop inside the while loop. This is going to happen. There's kind of two ways to think about it, right? So if the outer loop, the for loop, if this is going to happen V times, then hypothetically in the worst case graph, that's, like a strongly, well, not strongly, but like a completely connected graph, then when we pop this minimum element, every time it's going to have a connection to every other vertice. So we can kind of think about this like this inner loop happening V squared times, right? Or what we can do is we can say that it happens E times, right? Once for each edge. And I think that's a little bit more elegant. So let's say that this loop happens E times, happens E times. And if I lost you there, I encourage the astute amongst you or the curious to kind of think about this connection. Why is it that you can kind of rewrite E as V squared? Because this is totally legit. Why is that? But yeah, that's a little exercise for y'all who are here. So maybe think about on your own time, get some deeper understanding. So the picture that I'm trying to point is that the picture that I'm trying to paint is that we've got these two operations. One happens V times and one happens E times. And these are the expensive ones. So we can rewrite the runtime for Dijkstra's as, we've got this thing that happens V times however expensive it is, plus this thing that happens E times however expensive that is. And I just referred to the first one as pop because that's removing from the priority queue. And then I referred to the second one as update because relax updates the priority queue at each step. So hopefully what is now clear is that the runtime for Dijkstra's algorithm is actually dependent upon the runtime for these functions, right? We just, like, this is a composite function right here. What is pop, right? What is update? We don't know. And so we actually need to reference this table that we made earlier here to fill in the different runtimes for the different priority queue implementations that you might see. So if we have a heap, then both the pop and the update are going to be done in log time. So the heap runtime for Dijkstra's is going to be O of V times log V plus E times log V. And if that's confusing, go think about the section that we just talked about, come to terms with it. For a sorted priority queue, it's going to be V times pop, which is, what did we say was pop for the sorted? Said the pop was 1, which I think that makes sense. Plus E times the push, which what did we say was push? Said it was O of N. Okay, well, I guess N in this case is V. And then for the unsorted, it's going to be that, but completely backwards. So O of V times V plus E of 1. Okay, and so these are your 3 runtimes. I would be comfortable being like ready to rattle these off and recite them, kind of almost in like a memorization sense, but also kind of in an understanding sense, like understanding you've got like this frequency of occurrence, which in this case is V and E, times this expense of operation, which in this case is going to be pop and update. So hopefully that's clear. Okay, so let's actually look at Dijkstra's algorithm. So Dijkstra's algorithm is going to return the shortest path given a graph, right? And so maybe it would have been more wise of me to have written the full name of this problem, which is technically this is the single source shortest path, because we have to pick somewhere to start from. And like in all of our examples, we're starting at A just to keep it, reasonable and consistent. And so when we run Dijkstra's, we kind of, randomly, or at least arbitrarily so, pick a starting point. And from that starting point, we're going to run all of these steps that I listed up here. And I promise it's not this complicated. Like when you can do it by hand, you just, you have it. Like, you don't have to think about these steps. And then as we run it by hand in this table right here, we keep track of the state of the priority queue at each iteration. And in a greedy sense, we pop one of the nodes off of the queue, and then that becomes a permanent part of the path that we say is the shortest path from the starting node to any of the other nodes. Okay. So yeah, let's go ahead and reset this example. As you can see, I've drawn this graph right here, and the weights for the graph are all written in red. Notice how none of the weights are negative. This is actually non-trivial, and I could see that being a test question, is like, can you have negative weights for Dijkstra's algorithm? The answer is a resounding no. Okay, so first step for Dijkstra's algorithm, actually, let me reset, is to initialize everything. So on iteration 0, we don't pop anything, but we do initialize the starting point, which in this case we're starting at A. We're going to say that the distance to that starting point is 0 because we've already found it, and the distance to the other points is infinity, because when you haven't found something yet, the distance to get there is infinite because you can't get there. So should make some sense. So far what we've done in the algorithm is kind of this little chunk right here. This is kind of the first thing that we do in this table. Okay, so at the first iteration, we're going to pop the minimum element, which in this case you can see is A. And so we're going to pop A, and from A, we can see some of these nodes. And while it is true that these nodes already have paths that are marked for them in the queue, if popping from A and looking at the paths that come from A discovers a more efficient path than the one that is already known, that is when we call the relax function. That's when we update the queue. So A can discover B with a cost of 5, which I'm going to formalize like this. A can discover C with a cost of 9, and it can discover D with a cost of 2, I think I said. Okay, and then E is still undiscovered. And the superscript notation just means like this was like A is the parent of C on this path, And this is like a big test question that's going to come up a lot. So I'm gonna come back to this in a second. Okay. Anyways, the next thing we do is we look at the next minimum from the priority queue and we pop it. And hopefully that should help build some intuition, right? Like the reason we need a minimum priority queue is because we need to pop the minimum element. We need to have that available at every point in time. So the next thing we're going to do is we're going to pop D. So let's go ahead and remove these arrows. And looking at D, let's see. So D can discover C with a cost of 2 plus 4, which is 6. So find C. I'm going to say that that's better from D. I'm going to say that's better than our previous path, right? Because 6 is shorter than 9. D can discover B with a cost of 3, right? It's 2 plus 1, so 3 from D. And let's see, D can discover looks like E with a cost of 8. Yeah. Yes. Okay. And so now we're going to pick the minimum element again. We're going to pop that. So we're going to pop at iteration 3. We're going to pop B from the queue. So we're going to put that here. Go ahead and erase these arrows. Oops. And let's go. My bad. And let's go ahead and travel to B. So we went this way. Let's see. So B can discover C with a combined cost of yes, question?
Sorry. Oh,
Yeah. Oh, no question. Okay. So B can discover C with a combined cost so far we've seen 2 to get from A to D plus 1 to get from D to B plus another 2. So I'm going to say that's 5. So we found this, and then B can get to remove these. Let's see, B can get to E. No, it can't. So it's still 8 from D. And once again, we're going to pop the minimum element, which in this case is going to be C. So that's like going here. And let's see, so C can find E with a cost of 7, I believe. Right, because it's 2 plus 1 plus 2 plus 2. Yeah. And then our last iteration is just going to be popping the last element, which is E, and going here. Okay, and so if we draw our shortest path tree, just kind of preserving these blue arrows as we wrote them, we get this, which this actually serves as from A, what is the shortest path to any node. And as you can see, it's kind of like a single line. It's not always that way, but this is our shortest path tree. So some test questions that I could foresee being on a test would be like, given this graph, run Dijkstra's by hand, which, I think you should be prepared to do. Given this graph, like not given the graph, given like assuming we couldn't see the graph, what is the shortest path from A to B? So you'd have to be able to look at this table and say, use your hand to cover up the graph on the left, right? What is the shortest path from A to B? Well, we know it's 5 because that was the last thing that it was when it was popped. Or what's the shortest path from A to D? It's 2. Shortest path from A to E is going to be 7, right? Which is just the last known path at the time that the node got popped. Or maybe a more advanced question is like looking at this table only and not the graph. Like, can you tell me what the parent, like what the path from, let's say, E or C to A was, right? So given this table, we want to find the path from C to A. Well, we look at C. When C was popped, its parent was B. And when B was popped, its parent was D. And when D was popped, its parent was A. So you would like return something like this, right? So that's a possible test question. Be familiar with this, be able to do it by hand. I think it's not terrible. Okay. So we're running a little bit long on time. It is currently 3, so we've been going for about an hour, but I've got like, 15 minutes worth of stuff left, I think. So if you have to run, my feelings will not be hurt, but for those of you who can take some extra studying, we're going to keep charging. So the next kind of category of minimum spanning tree, like this is kind of a category that falls within advanced graph algorithms, I think. The first algorithm that we're going to look at is Kruskal's algorithm, which I think makes a lot of sense, especially when you need to do it by hand. It's very intuitive. So given this graph that I listed here on the left, we build what you can see down here, a minimum spanning tree, which is the graph that connects all of the components with the least sum edge weight, right? So on the test, this might, they might be cheeky and say like, we're building bridges amongst islands and we want to use the least amount of material to connect all of the islands, or whatever it is, or like, cell phone towers, or whatever trick they use to obscure that it's a minimum spanning tree problem. This is what the spanning tree looks like. And given a graph and a set of weights, can you determine what the most efficient way to do this is? And it turns out we've got some algorithms to do that, the first of which is Kruskal's. And I'm going to go ahead and reset this problem. So Kruskal works by taking in a list of all of the edges that exist on a graph, sorting those edges by weight, and then in a greedy fashion, adding the least expensive edges to a set so long as those edges contribute to the unification of disjoint sets. So that's kind of a hand wavy thing. That's kind of like a take my word for it answer of what's happening. But really what's going on is, to start Kruskal's algorithm, you make a disjoint set that represents every individual node in the graph, which in this case is going to look like A, B, C, D, E, F, so on, right? I'm not actually going to draw them at first. And then say you discover an edge from B to D, well, you're going to call union on that. And now you've got this edge in the same set, and so on and so forth. And so there's going to be some operations that we run into in Kruskal's algorithm. So imagine we had 2 sets that look like this, and now we discover, let's say we discover some wonderful edge from C to D, and we want to use that in our spanning tree. Well, instead of connecting C and D like we did before, we have to connect the set that contains C and the set that contains D, and we'll have one big set like this, like that. And so doing Kruskal's algorithm, there's kind of like 3 different operations that we need to have, but I'll talk about that in a second. Let's just do it intuitively. Let's do the like by hand method first. So what we're gonna do is, just looking in our head, we can sort these edges. So the first edge that we're gonna see is F to H. So let's go ahead and put those in a disjoint set. So F and H. And we're going to keep going. So the next edge we're going to find is A to C. So A and C going to be in their own little set. The next least expensive edge is going to be this one from D to G, I believe. So we've got D and G in their own little set here. And now we have a choice, right? So we could either do this one next or this one. But these letters are smaller, so I'm going to randomly just pick this edge. So now what we need to do is we need to connect the set containing A and C to the set containing D and G, because we found an edge connecting these 2 sets. And as you can see, that's going to look like pretty much the example that I showed before. I'm just going to write this as one big disjoint set. So now we've got, as you can see, this first set right here, this disjoint set, kind of representing this little region of the spanning tree. And then we've got this disjoint set kind of representing this region of the spanning tree. So maybe that, helps make sense why it is that union is an applicable thing to do for this type of algorithm. Okay, so moving on, the next least expensive edge is I. So let's go ahead and add I to this disjoint set. So that was all the 3s. Okay, now we're going to run into something interesting. because this edge actually right here from A to D is not useful, right? A to D would give you a union between A and D, and as you can see, they're already in the same set. And our goal from Kruskal's algorithm is to eventually get some kind of set such that we include all of the nodes and happy day, right? So adding an edge that just gets you two nodes that are already in the same set doesn't actually give you any progress towards our ultimate goal. So I'm going to mark that one as yellow, meaning that we didn't use it and it wasn't useful. The next edge we're going to look at turns out to be useful because it's connecting this set to this, as of now, unused part of the tree. So we're adding B to this set, like so. And let's see, the next edge, that was all the 4s. So we've got a 5 here from E to B. So let's just go ahead and add E to this set. And then there's seems to be an edge from E to H. And as you can see, E is in this set and H is in this set. So to combine the two sets, we need to actually union the two of them. We did before. And I don't think I could fit this on one line. Just gonna call it like that. Okay, and now all of the edges are in the same set. As you can see, I believe. And it looks like, oh, also there's a useless edge here for anyone who's astute and paying attention. I clearly was not. But now that everything is in the same edge, that's like saying everything is in the same tree, and the tree looks like this. So a quick note, the tree, the minimum spanning tree is going to end up with, every single time it's going to end up with v-1 edges, right? Because like, you can just kind of prove that, right? Tree with 1 value is going to have no edges, or with 2 values, it's 1 edge, 3 values, it's 2 edges, so on and so forth. And a note on the running time. So given this algorithm, we're going to have to call this operation called make set v times. So make set was like when we had 2 disjoint sets, and we just, made them, right? We say like, oh, we've got this node A, put it in a disjoint set, make the set. So that's going to happen v times because there are v vertices. Find set. So find set is going to happen 2 times e times, which again makes sense because for each edge that we're looking at, right, it is potentially the case that we have to find the set that this vertex belongs in before we can do any kind of union operation. And then for union, that's going to happen v-1 times, because it's going to happen kind of like once for each of these connections that we add. So there's more information about this on the slides. Probably good to know these things. And then overall, our runtime is going to be O of v plus e log v. There's a proof for that in the slides in the doc that I linked, but I'm not going to do it. Just take my word for it, or go find it yourself, whatever suits your curiosity. And then I was going to do this example of prims. I'm gonna go ahead and do it. If y'all are tired and fatigued from all of this review, I am as well. You're not wrong for having taken in a lot. So Prim's algorithm. I'm gonna actually speed run this algorithm. Okay, so imagine we've got this graph here on the left. This is also a minimum spanning tree problem, and we can actually get the exact same output that we would have gotten from Kruskal's algorithm by just running Prim's instead. Prim's is remarkably similar to Dijkstra's algorithm, except the criteria for which we add things to the priority queue is we add them based on the least expensive edge we found, not the cumulative path from a source. So A, B, C, D, let's see that a little bit, E. So at iteration 1, it's very similar. We're just going to initialize it the way that we used to, and we're going to pop the minimum, which in this case is like doing this. Okay, and so as soon as we pop the minimum element, you can see we can now update some of these weights. So we can find B with a cost of 3. We can find oh no, B with a cost of 10. I'm tripping. I'm actually tripping. And we can find C with a cost of 3. and the other ones are undiscovered. And we're going to pop the minimum, which in this case is C. So, oh man, that's terrible, y'all. I'm so sorry. Why did I do that? Speed run, maybe not a great idea, whatever. Pop C, and that takes you here. C discovers B with the less expensive edge. So let's go ahead and take note of that. C discovers D with an edge of 7, and E is still unfound. So we're going to pop B will be the next thing. It's like going here. C3, B, and B can discover E with an edge of 6. So 6 from B. And let's see, D is still, best we can do is still 7 from, oh, what? This should have been C. My bad, y'all. 7 from C. And then now we're going to go ahead and pop E. And so, you know, even though we've got this 0 term here, like you would think we would have used it, I think, but I guess we haven't used it yet. We have to discover it, right? So like this is kind of like the big difference between Kruskal's and Prim's algorithm is kind of the order in which you discover these edges, right? So you would think that like, actually, let me just go ahead and finish out this table. So for E, pop E, and then from E we can now discover D with a weight of 0 from E. So you would think like in Kruskal's, this would have been the first thing that we did. Like we would have found this first, and you know we would have started with that being the minimum edge. But in Prim's, it takes us until the very end of the algorithm to find that, and then the last thing we do is we pop D and get our spanning tree. Okay, and that's gonna look like A, B, C, D, E. Yo, I am wiped. That was so much effort. Okay, cool. So as a quick little recap, and by the way, everything I just did in the last 10 minutes also fair game for test questions. Quick little recap. Basically, all of graph traversal is dependent upon these two algorithms being DFS and BFS. You can kind of think of them as like almost like brothers, you know, or maybe cousins, something like that. They do almost exactly the same thing, except they use different data structures, one being a stack and one being a queue. You can break a graph into strongly connected components, and there's some rules for how you do that. When you run DFS, you get an output that's a tree, and all of the edges that don't belong on that tree get classified differently. Top sort can be done with n degree, or it can be done with DFS. There's 3 different ways to implement priority queues. They all have different, you know, trade-offs and drawbacks. You can use a binary heap as kind of a compromise between the two. Dijkstra's algorithm, the pseudocode looks like this, and its runtime depends on these red lines that I decided were expensive. And I listed out what those runtimes actually are when you figure them out. When you run Dijkstra's algorithm by hand, you should get this helpful little table on the right, which gives you all the information that you need to know about what happened on the graph on the left, and that gives you the shortest path from that node to all the other nodes. And then Kruskal's algorithm uses disjoint sets to find the minimum spanning tree on a graph, and Prim's does the same thing. Yeah. Okay, well, that's all I had. I think that's pretty comprehensive. You know, this might not be everything you're going to see on the multiple choice, but I think it's a really good start. So let's see. Stop sharing, stop mirroring. Cool. Shares, stop share. Who has questions? See, you can see the chat now. Oh, it looks like y'all are very active in the chat. Excellent. Yeah, so some good stuff here happened in the chat for sure. Okay, anybody have like out loud questions that they'd like me to answer?
Oh, hi.
Yes.
I see that in your note, the DFS, you have some numbers on the graph. So what's that mean? Like when you construct it?
Good question. So the DFS, those numbers represent the order in which you find the nodes, right? So like if you look at that example, and I'm going to post this on YouTube, those numbers, 0 means that that's the first thing that you visit, and then 1 is the next thing you visit, 2, so on and so forth. And when you turn around, or like you complete the recursive call and you walk backwards, you say that, like, you know, if you're on like 3/4 means you visited the node as the third thing you did. You terminated DFS as the fourth thing you did, and you walked backwards. So good question.
This test is only over the graph-related topics, right?
Yeah, it's graphs, and I would be prepared to do hashing, but I think hashing is relatively kind of straightforward. I'm gonna be like completely straight up with y'all. The test hasn't been made yet. So like this review that I just did would make you very, very prepared for the old test that we had on our test bank. For whatever reason, we just haven't finished making the next one yet. So I can't actually say for sure because I don't know. Like usually in these reviews, I actually read the test first. That way, when I'm like, hint, hint, you need to know this thing, it's because like I've seen the question and I know y'all need to be prepared. So this is kind of based on old material, but I'd say if you're comfortable doing what I just did, and then you watch Josh's video on the FRQ coding, and you do like 1 or 2 of those problems, you should at least get an A, I think.
Can you talk a little bit about like any differences between prims and Kruskals? Like if that could be like a test question.
Yeah, excellent question. So, the differences between prims and Kruskals, I'd say the biggest one probably is, well, they should both give you the same answer, hypothetically, being like, they should both give you the same summation of weights. They might not give you the same spanning tree, and they might create that spanning tree in different orders, right? So, the minimum spanning tree created by Kruskal's algorithm is going to take like a greedy approach in taking the least expensive edges, and Prim's algorithm is going to take a greedy approach in starting at a node and taking the least expensive edges from that node. So kind of 2 different approaches. Kruskal's is more like the discrete math, like the 222 style solution of the problem, and Prim's is very much so like the graph solution to the problem. They both have the same running time, both kind of work under the same conditions. I think they'll both be O of V plus E log V. Prim's is basically Dijkstra's, very, very similar. Kruskal's is kind of like its own thing. And then also Kruskal's relies on a bunch of extra operations. Like we don't really cover set as a data structure in this class, but to run Kruskal's algorithm, you've got to have like the ability to do union find, which is its own algorithm. So if you're curious about that, I think there's videos on YouTube explaining like this is like you know, bijection or union find or whatever it is that they use to actually implement it. Good question though.
Is the only thing we have to know about like Bellman-Ford is that it can be used on like graphs with negative weights?
Yeah, I think so. That would be my takeaway from it. So there's going to be like, you know, a few algorithms on the test where it's like the most I would expect to see would be, you know, just like a one-liner question, like when is this useful? So for Bellman-Ford, yeah, I would understand that it can, you know, handle negative weight cycles. I would also understand that its runtime is O of V times E, so it is usually worse, usually less effective than Dijkstra's. Dijkstra's is kind of like an edge case, right? Like the edge case in which the graph looks a certain way, you can actually do it faster, whereas Bellman-Ford is kind of like the general case. So yeah, be prepared. Like I would at most see like 2 or 3 questions. They won't ask you to do it by hand. They won't ask you to you know, like label the pseudocode, even though you might see the pseudocode, maybe, I think. And then the other one that comes to mind is the Huffman data compression algorithm. So I didn't cover it at all, but it is like hypothetically they could say like the Huffman the Huffman algorithm does what? And you know the answer is compresses data. Or they might say, is the Huffman algorithm a greedy algorithm? And I think the answer is yes. Or they might ask like, does the Huffman data encryption algorithm result in a loss of data? And, you know, in which case it's no. But again, all of the responses from you are just like essentially one-liners. So for those 2 algorithms, and maybe I'm missing something, basically just a general understanding should suffice. Good
Okay,
question,
thank
though.
you.
Yeah.
if I recall, I think there was a scenario in which topological sort can't be applied.
It doesn't come to mind. It sounds familiar. Top sort not being able to be applied. I'm gonna take a look at that. I don't remember what case that is. When I was looking over the old tests, I didn't see that as a question. It might be a question. So y'all who are here, figure out the answer. That's your homework. I'm also gonna figure out the homework. So good question. Y'all figure that out. See, I hope I'm pronouncing this yet. Jinyu says, may only work on directed acyclic graph. I suspect you are correct. Because I believe if you have a cycle and you're running top sort, that messes up the way that you compute the n degrees. I see what I'm not comfortable saying is if that changes the implementation for the DFS based, which is kind of why I held my tongue. But yeah, Jinyu, good point. Excellent point. I think you might be right. But yeah, y'all verify that, please.
Of all the algorithms that we're going to be tested on, are any of them not greedy algorithms?
I would say I wouldn't call BFS a greedy algorithm. Yeah, I wouldn't really call that a greedy algorithm, honestly. I wouldn't call up heap and down heap greedy algorithms. Yeah, it's mostly greedy algorithms though, the vast majority. Like Dijkstra's for sure, Kruskal's for sure, Prim's for sure. Yeah, good question though. Anything else? See, Hannah says thank you. Yeah, I'm sensing silence from the room. So thank you all for sticking with me. This was like a lot of information to take in all at once. If you've made it this far in the course, I absolutely believe in you. Do what you got to do to get that A. I'm not going to say you deserve it yet. You will deserve it as soon as you've earned it. And I believe everyone here is capable to get that A, that B, that C, whatever that letter grade that is that they're shooting for. Best of luck, y'all. It's been a great semester. If you have anything, feel free to reach out. I'm happy to answer any emails, any questions, whatever it is as you're studying. Be sure to figure out when your final time is so you don't miss it. Yeah, with that, have a nice dead week. Adam says thank you. Yes, thank you, Adam. Thank you, Elim. Thank you, everyone who's here.